So what InfraSend is doing, the InfraSend architecture is sketched out here. So it takes as input two sentences. One is the premise, the other one is the hypothesis. Then out of these sentences that come in as a stream of words, a sequence of words and another sequence of words, this sequence of words is mapped somehow to a vector u. And the same here, this hypothesis sentence is mapped to a vector v. Then in the next step, it concatenates these. It concatenates the different representations based on u and v. First u and v itself, then the absolute difference. So you take u minus v. So these are two vectors. You can make the difference. Then do the element-wise absolute value, and then also the element-wise multiplication. From this we get, like, this is a 4000 dimensional representation, this is also a 4000 dimensional representation, so we get 4 times a 4000 dimensional representation. This is 16 dimensional. This is fed through a couple of connected feed-forward layers, and then we finally do the softmax prediction, which is neutral, entailment, or contradiction. And why it's doing these operations down here? Well, it's just assembling more information signals, which then may be helpful as information for the subsequent layers and for the classification task. And important to note is that when InfraSend is encoding the premise and the hypothesis, it's doing that using the identical network. So here's a network down here that is encoding both of these sentences into vector representations, but these are identical. These are identical networks, right? So no matter whether you feed your sentence in here or your sentence in here, you will get so no matter whether the sentence appears here or here, it will get the same representation if the sentence is identical. And after InfraSend has solved this supervised classification task, you forget about the classification task. So this classification task is not of interest anymore, but what is of interest is this 4000 dimensional representation down here. So basically, only this part of the network is kept. You feed in a sentence, you get the representation out, and note that by the property of being identical, it doesn't matter whether it's this part or this part of the network, because they are identical. And this then is the sentence embedding, right? You feed a sentence in, you get the sentence embedding. Now the final question is, how do they get this lower part here? How do they encode the sentence into a vector representation? What they use is an LSTM. That's a variant of the RNN. We've already seen the RNN today. And they use an LSTM. That's a better variant of the it's a special case of the RNN, which is a very good model of RNNs. And this LSTM is also bidirectional. What that means is you do not go into one direction, but you go independently also in the other direction. You have the RNN that goes from left to right. You have a second RNN that goes from right to left. You concatenate those representations, those hidden representations, and then they do max pooling. So basically they concatenate that. This becomes a vector, that also becomes a vector. They get a vector at each time step, and what they do is they do the max pooling over time. So basically they compare those 4 elements and find that this one is the biggest. They compare those 4 elements, find that this one is the biggest. They compare those 4 elements, find this one is the biggest. They combine those 4 elements and find this one is the biggest. Then they out of these maximum elements, they construct a new vector, and this vector u is finally the sentence embedding, right? Yeah, so this is how the InfraSend architecture works. Good. So we have seen three different embedding techniques: InfraSend, which is a supervised model, and 2 unsupervised models: skip thought and sequential denoising autoencoder. Both of these models, all 3 of these models, have been based on RNNs, recurrent neural networks, and in this sense they are complicated and they are complex and they are costly, because if you feed in a sentence into inference, it has to go through this RNN here, so through this recurrent neural network, and this is a costly operation because you have to do all of these vector matrix multiplications. It's also recurrent in nature. You cannot parallelize that easily. Uh, so basically, this is what we call a costly or a complex sentence embedding. So concurrently to those complex models, people have also proposed simpler and cheaper methods. And what are these simpler and cheaper methods? Let's have a look. So the previous models that we considered, to recapitulate, are costly because as a test time, you'd have to run them through an RNN, and there are many matrix vector multiplications involved, and this may be slow and memory intensive. So the first such model is the Sami-Sibo model that has been proposed in 2016. The goal is we want to have average word embedding model because this is really costly to have at test time, but we change the word embeddings in a certain way such that they give good sentence embeddings, right? And let's look at the model. So in comes a sentence here, that's sentence I. And then we also have the previous sentence and the next sentence. That's a little bit like the skip thought model. So the idea is like sentences which are close by should be semantically similar. And then we have another idea like negative examples. That's like in the word2vec model where we have unrelated sentences and just randomly drawn, and we say they should not be similar. So what we do is we have the words in these sentences. We assign them some random word embeddings. So like the word embeddings are they are learned to the task. So we don't take them pre-trained, but we train them ourselves. So we assign each word a word embedding in all of these cases. Then we average those word embeddings, right? So we just take the simple average word embedding. Then we compute the cosine similarity of all of these averages. So we take the average here, we compare it to this one, we do a cosine similarity on these two vectors, so we get a number here. We compare this sentence also to this sentence. So we compare the focus sentence. So this is our focus, the target sentence. We compare it to this word, to this average. We compare it to this average. We compare it to this average and to this average. So we have 1, 2, 3, 4, and we have here 1, 2, 3, 4, 5. And why do we have 5? Well, because here in the middle is also something that we have skipped. So you see that like this box here has nothing, but this is just because this could be arbitrarily long here. So we compare this average to all of the other averages. We get a vector of cosines. We make a probability distribution out of this vector of cosines to get a probability that says how likely each of those sentences should be. And what is the target to the model? The target to the model is the true vector is is like you put a 1 here for this sentence because that is a sentence that should be close to this target sentence. So the previous sentence should be close to the target sentence, and the next sentence should also be close to the target sentence. So you put a 1 here and you put a 1 here, and because they should be similar, but those two here, they should not be similar, or all of those should not be similar. So you put a 0 here. So this is the truth that we want to predict. We want the model to say this is a similar sentence and this is a similar sentence and these two are dissimilar. Now if we put 1 ones here, that doesn't quite work because it has to be a probability distribution. So we divide by 1 over 2. And in general, yeah, so we divide by 2 because we have two sentences that we consider to be related sentences, so we divide by 1 over 2. If it were 3, would divide by 1 over 3. So that is what the model is doing. It's constructing word embeddings in such a way that the average word embedding that we get should have the property that similar sentences, and these similar sentences are given here by the set st. It is in the model's case is the previous and the next sentence, should be close, and dissimilar sentences like random sentences, which we call here the set s minus, they should have different average word embeddings, right? That's the model. And then what happens now, people train this model, and after they have trained it, they find out that the function words have very low vector norms, so they are close to 0. So what are the function words? Function words are 2, of, and the a. So these are articles, prepositions, etc. So they find that those have very low vector norms, and this makes exactly sense, because if the average word embedding should only take into account semantics, and then we should discard all those words that contribute little to semantics. So that's a cool thing about Siamese-SIBO. Now, if you would want to criticize this model, then you could of course say we could also get this by just taking a weighted average of the word embeddings instead of the plain average, where the weighted average gives low weight to all of those words, right? So that could be a critique of the model that yields a much simpler model, which may perform quite similarly in downstream tasks. Another model has been proposed by ourselves. So our idea was, we had actually two ideas. So the first one is, people always only took the average word embedding, right? So they have, if they have a sentence with 10 words, they take an average over 10 words. Now, average, there's a the word average has a intuitive popular interpretation, namely you add 10 things and you divide by 10. That's also called the arithmetic mean, right? But in mathematical theory, there are a lot more ways how you can do averaging, and what mathematicians call averaging. And these different ways are often subsumed under the term power mean or generalized mean. And this power mean is given by this formula here. So if you have n numbers or n vectors, if you have n numbers or n vectors, or let's say these are n numbers, so we do that afterwards on each component of vectors independently. If we have n numbers, we get a power mean with vector p, with like parameter p, in this way, that we take each number to the pth power, we sum that up, divide by n, and then take the root 1 over p. And there are several special cases. Namely, if you take p equals 1 here, you just get the standard arithmetic mean, right? This is what people are typically using, the arithmetic mean. Now, if you take p equals 2, you get a quadratic mean. If you take p equals 0, you get a geometric mean. If you take if p goes to minus infinity, you get the minimum of those numbers, of those n numbers. If you take p equals plus infinity, you get the maximum. So basically, depending on how you parameterize this p, you get out different means that mathematicians have proposed, right? So this is our first idea. We cannot only do a standard. We cannot only do a arithmetic average, but we can do many different averages. And so what we do is we go over each word embedding dimension, and we consider an average over that dimension, and we do not only take the standard arithmetic average, but we can also take an arbitrary power mean average, right? And then then we can concatenate those different power mean averages, right? So we can take the standard arithmetic mean, we can take the maximum and the minimum mean, and we can take the geometric mean, for example, or the quadratic mean, and we can concatenate all of them. So each mean gives a different summary of a series of number or of a sequence of numbers. So we get different summaries of these numbers, and each one has different information signals, right? So this is the first idea. Instead of just taking the average mean, the standard arithmetic mean, we take different averages and concatenate them. The second idea is we can also concatenate diverse different word embeddings. So we take the word2vec embeddings, we take the cloth embeddings, and we take fast text embeddings, and we concatenate them. And all of them also, they have different information sources, right? So these embeddings contain different information signals and are trained on different sources also. So they also have hopefully complementary information. And by doing a concatenation, we keep all of that information so that downstream models that build on our vectors can have the full range of information signals available. And if you want to see this in practice, what we can do is, for example, we have three words. We take the cloth vectors. We look up the word embeddings in the cloth. In the cloth embedding file, we look up the same words in a different vector space. In this case, it was called attract repel. We do that for each word. We concatenate that. So we get like vectors of size 6, and then what we do in one case, we can take the mean of this vector of size 6, so we do a mean over each dimension. So we do a standard arithmetic mean over each dimension. So this is 1 plus 1 minus 2 is 0, 2 plus 2 is 4, minus 1 is 3, divided by 3 is 1. So we get the arithmetic mean, and we get the maximum. So at each dimension we take the maximum. This is 1, this is 2, this is 3, right? So this is the maximum, and we can do other operations, and then we concatenate that and get the sentence embedding out. Now there's a final model that I want to introduce, mostly for historical reasons, not that it works particularly well, but it has been introduced as one of the first models that does not only encode words but whole longer sequences, such as sentences and maybe whole vectors, has been introduced by Thomas Bigelow's team in 2014. The paragraph vectors, the idea is to assign a paragraph, which could be one sentence or maybe several sentences, a vector such that we can predict words in the paragraph or in the sentence, right? And this is also a model that is kind of inspired by the SIBO and skipgram model for word embeddings, right? And the architecture could be, for example, let's say this is the analogy to the SIBO model for word embeddings. Like in the SIBO model, we get in the words as input. We embed them into vectors, and then we want to predict the center word. Now in this case, they predict the next word maybe for no good reason, but they change the architecture a little bit here. And in this paragraph vectors model is we also have an ID. Now here is not only the IDs of the words, but we also have an ID for the sentence or for the / paragraph, right? So we can also say this is the 7th sentence. We have a paragraph embedding or a sentence embedding matrix here. We extract the row that contains the sentence for this paragraph or sentence, and then we have the representation here, and from this representation we concatenate, or we average all of the representations, and then predict the center word or maybe the next word. And then the idea is, of course, sentences or paragraphs that are similar, they would also have similar words, so they would get similar representations here. And you can do the same with the skipgram kind of analogy model where you get the idea of the sentence and you want to predict a sliding window of words that occur in that sentence, right? And the important thing to know is that this paragraph vector is shared across all contexts generated from the same paragraph. So you have a context here that's generated from the paragraph. That could be the first 4 words. Then you predict the next 4 words, the next 4 words, the next 4 words. And all of these, of course, have the same IDs. So you say this is always the same paragraph. But if you go to the next paragraph or the next sentence and you predict words again, then the ID will change, right? So that's the meaning of being shared or not shared. Whereas the word vector matrix, uh, the word vector matrix is shared across paragraph, meaning that if you have this word vector matrix, no matter in which paragraph you are, you see the word the, then it will always be the same, no matter in which paragraph you are. But as soon as you change the paragraph here, then of course it will get a new index, right? So this index will change, but the index for the word the will always be the same. Good. So these are 3 models. So we have seen 3 complex models and we have seen 3 simple models. For inducing word embeddings, the simple models have the advantage that that they do not have to run the input word vectors through an RNN, but they just do averaging. At least in 2 cases, they do averaging. So in one time, this is this complicated averaging where you learn word embeddings to the task, then you average them, and you induce word embeddings such that their average is a good sentence embedding. The other method is like extending the notion of averaging to other kinds of means, and also concatenating different kinds of word embeddings, which each contain different kinds of information, such as cloth, attract, repel, fast text, and maybe dependency-based embeddings, right? To have like really different embedding types. And the third one, well, this is a model that is based on analogous principles as the word-to-vec model. Um, it is also computationally easy to get. Once you've trained the model at this time, you will just look up the sentence embedding in a matrix, right? Rather than doing like matrix vector multiplications as you do in an RNN. Good. So we have seen 3 simple, 3 complex models to induce word embeddings. Now let's look into the evaluation of sentence embeddings and maybe also look into problems with the evaluation of word embeddings. So the evaluation is similar as for word embedding. So we have 2 kinds of tasks, extrinsic or intrinsic. The extrinsic means we feed in the embeddings to some task. And where we have some task, we encode all of the sentences in the task. Like we want to do some classification task, such as document classification or sentiment classification. We embed all the sentences in our task, and then we take these vectors and train a simple classifier on top of the embeddings, such as logistic regression, right? And then also we have the intrinsic evaluation, where we do not feed in the embeddings to some classifier, but instead we directly compare the embeddings using, for example, cosine similarity. So the general scheme is you take your sentence embedding model, which we would also call nowadays sentence encoder. You embed each sentence in an extrinsic task. You train the classifier on the embedded sentences, and then you repeat with different kinds of sentence embeddings, and then you check which one gives better results, right? And if embedding A gives better results than embedding B, then you will say that A is better than B for this task. So which tasks are there? Like a standard array of tasks has been developed by Alexis Conot, who is a researcher nowadays in Facebook, I guess. Um, so in one of his in the InfoSend paper, they have developed this standard set of tasks, which is, for example, movie reviews, customer review, classification, subjectivity, track, and sentiment classification. So here are the labels. So most of them are actually sentiment classification tasks. For example, here you have you have a sentence you want to say, is that positive or negative, and here the label would be negative, where the sentence is like too slow for a younger crowd, too shallow for an older one. That's a negative sentence. Uh, Customer review is also like, again, sentiment classification. We tried it out Christmas night and it worked great, so that is a good product, so the positive classification. Subjectivity is whether the sentence is subjective or objective, such as a movie doesn't aim too high, but it doesn't need to. That's a subjective statement. Then the track task is, you say, what kind of question is that? So you have to you classify questions. What are the twin cities? So this is a question about location. And then again, we have another sentiment classification task. So these are like standard tasks to evaluate sentence embeddings. Now to briefly discuss the intrinsic evaluation. The scheme is here: you take your sentence embedding model, you embed sentence pairs in an intrinsic task, use the cosine similarity to measure the distance between pairs, and you correlate that with humans. So the difference to downstream task is we directly compare the embeddings. We don't feed them into a downstream task, and we don't learn a model on top of the embeddings, right? And here are two tasks. So these two down here, SIG, relatedness, and STS. These are two intrinsic tasks. You have two sentences. In each case, you embed these sentences, and then you take the cosine similarities between the embedded vectors, and you correlate this to the human labels, right? So these are the two tasks here, and these two up here are actually not intrinsic tasks. Uh, Only these two down here would be called intrinsic tasks. So that's how you evaluate that. So what is the problem with the evaluation? So one of them is, so the different researchers come up with different, they propose different models, and at the same time they also their models have different sizes. So some embedding models are only 300 dimensionals, others are up to 4,800 dimensional, and then even larger, right? So the comparison may be unfair. You, if you compare something that is of low dimension to something that is of high dimension, then it's possible that the low dimensional is just as a disadvantage, just because it's of smaller dimension. Because, for example, a logistic regression is typically used as a classifier to evolve that to evaluate sentence embedding. Now, logistic regression is like a linear model, and depending on, and we know that if data is in a larger dimensional space, it becomes easier to linearly separate the data. So high dimensional data might be at an advantage by itself. So this is the first thing to keep in mind. Are you really proposing a better method, or do you just use a higher dimensional vector to encode your data with your new method? A second thing to keep in mind, that different models are trained on different data sets. So some are trained on Wikipedia, others are trained on the Toronto book corpus. So again, here's a similar thing. You have you propose a new model, but you also may change its training data. So if you change the training data, then this may have a huge impact on the performance of the model. And the final thing is, which classifier should we use on top of sentence embeddings in intrinsic tasks? So people mostly use a logistic regression, but you could use a variety of different other classifiers like multi-layer perceptron, or more standard classifiers like random forest or naive Bayes. So so how stable are your results over different classifiers? So this is a question that is not very well investigated, um, to my knowledge. So it could be that a different classifier would give a different ordering, would say like embedding B is better than A. Uh, um, then if you just use logistic regression, and then this of course calls your results in question if classifiers do not agree on the superiority of or on the uh, on, on the aspect which embeddings are better, right? And to look into the sizes question, there's a model of there's a paper of Witting and Kiela, which is your mandatory paper in this lecture, where they say, okay, we try in higher dimensional embeddings. So here they have different sentence embeddings, and here are the different tasks, such as movie review, customer review. And what they do is they increase the size of the embeddings, and you see that there's a general trend that results get better as your models, as your embeddings get higher dimensional. So if you compare this model here with size 24,000 dimension, and you compare it with this model down here with size 512, you will see that, okay, this or we can do it vice versa. We take this model here, which seems to be a little bit worse, but if you compare to this, but if you evaluate at size 25,000 and you compare it to this model here at size 500, then just by mere size differences, this model will be at an advantage. And we also have a similar paper where we say, okay, we have different competitors here, such as the power means models, the InfraCent model, and maybe Centuvec, so other different competitors. They all come with their sizes, like InfraCent is very large dimensional, P-means is lower dimensional, Centuvec is still a lot lower dimensional. So they all have different sizes, and these are their scores. These are their average scores on some task. Now we compare them to average word-to-vec embeddings, and these average word-to-vec embeddings, we let them range over different sizes, and what you see here is as we increase the size of our word-to-vec embeddings, they perform better. It seems to level off at some size, but importantly also they can compete some competitors which have been claimed to be better, but if there's a fair comparison, let's say at size 700, then already our average word-to-vec embeddings are on par with a couple of uh, competitor models that have been proposed as improvements over the average word embedding model, right? Good. So this is this part evaluation of sentence embeddings. Now we come to introspection of sentence embeddings. So this is also an important question recently. Why is it important? Because these sentence embeddings, well, you encode whole sentences. Sentences are long and they contain a lot of elements, and the resulting vector embeddings, the resulting sentence embeddings as a consequence are also usually very high dimensional. So we would actually like to know what kind of information do these high dimensional vectors encode, right? So we want to look into those embeddings, and this has been a trending topic in NLP and machine learning in the last 1 to 3 years, because people want to open the black box of deep learning, right? Deep learning is considered to be a black box, in contrast to some of the traditional machine learning where you define features, so you know what your model is actually doing. In contrast, like in deep learning, you do not know what your model is doing, right? It can learn anything. You don't have to specify the features by hand, so it's doing it by itself, but because it's doing it by itself, you also do not know anymore what it's doing. So we want to look into those. So we could test, for example, people have come up with something called probing task, and in this probing task, they task what linguistic information is captured in the sentence embeddings. Do they capture information about length, how long the underlying sentence is? do they capture information about word order? So um, whether two words, well, do they capture information about the order of the words in the sentence, or do they ignore the order? So we already know there are some models that ignore the order. Like if you take as the sentence embedding an average word embedding, we know that this does not encode order. You could also query whether they store information, whether a certain word is contained in the sentence. So do they store lexical information about the words that are contained in the sentence? Or you could ask yourself whether they encode agreement between subject and object. So can they do they store something that, like, this is a she likes cat is has agreement between the subject she and the likes verb, versus versus the sentence she like cat, where there's a error of agreement, right? So she and like do not agree anymore, the sentence is wrong, and we would like to know whether such information between pairs of words is stored somewhere in the embedding, right? Uh, and we do not know this from extrinsic or intrinsic tasks, because they are complex tasks and they may contain several knowledge nuggets. So movie reviews may require a mixture of all of these information pieces, right? If you want to know whether a movie review is good or bad, it could be that it contains certain words. So maybe if it contains bad, then it's a negative movie review. But it may also be that the length is important. Maybe short reviews tend to be good ones, and long reviews tend to be bad ones, right? So if we solve this task, we do not really know uh, which knowledge is required to actually solve this task. So it may be a lot of different information that is all intermixed, so to speak. And if we define those probing tasks, so these are like artificial tasks, we can clearly separate the different information nuggets contained in the sentences. And these probing tasks are there for introspection, so you can help interpret the sentence embeddings, because now you can say, okay, uh, these these embeddings basically store this and that kind of linguistic knowledge. Here is shown some probing tasks that have been defined. Bicram shift, for example, whether two words have been inverted. So this is my Eve Christmas, that's an inversion. This is so to speak a wrong sentence, and the word order of these two words has been changed into incorrect word order. Then there's the popular sentence length, where they predict the sentence length among 6 classes. So this um, is the classification task is not in exact number of words, but in length classes. So I can't wait to show you and Mr. Taylor. So this is between 9 and 12 words, so that could be the third length class, so to speak. And there are a couple of others. So word content is the one that I've already introduced. So here there would be a sentence, and then the model has to predict which one out of 10, like out of a set of words is contained in the sentence. So there's a set of words that the researchers propose, and then they check whether each of those words occurs in the sentence. And there are a couple of other probing tasks defined that we don't have to go into here now. Like, for example, present tense is whether the main verb in the sentence is in past or present tense. So you have the sentence, she smiled at him, her eyes allied with love, and the label is present. No, that's actually wrong, right? So it should actually be past, if I understand that correctly. Because that's not present tense, right? So to conclude this, we do a final exercise, like a small thought experiment. We look at we look at average word embeddings, and we check whether they could store, whether they can store order. No, they cannot store order. We know that already, because by averaging, no matter in which order the words in the sentence appear, they will always have the same embedding, so they will not store, they will not perform well on the order probing task, so they will perform very badly on this bigram shift here. Can they do well on sentence length? Yes, they can do well on sentence length. And why they do well on sentence length? Because by the law of large numbers. So we know that if you add n numbers and divide by n, and if n becomes very large, then we know that by the law of large numbers, this converges to the expected value, right? So assume your numbers, your n numbers that you add, they all come from a similar distribution, right? So they will go to the expected value, right, of this distribution. And now if we do average word embeddings, and the word embeddings are all centered around 0, let's assume, and this is often the case in reality, they're centered around 0. So if you average them, your average sentence embedding will be the 0 embedding, right? So it will just be it will just go towards 0, and the closer it is towards 0, the more likely it is that the sentence is very long, right? So it can store sentence length, it cannot store word order. Can it store whether a certain word appears in a sentence? This is a question I will leave up to you for maybe the exercises or maybe the exam. Okay, thanks a lot. So this concludes our third lecture about sentence embedding. The mandatory reading for next week is this paper here, where they show that many of the complex models that have been proposed are good, are better than the baselines, but maybe this has been because they were very large dimensional and the baselines have been lower dimensional. And this paper also shows if you make the baselines large dimensional, then maybe the baselines perform quite well, and you can even do this. You can get this by various factors, like just multiplying the base word embeddings by large matrices in an RNN which has not been trained at all. So it's an untrained RNN, and you just feed that through such a large RNN, and the base word vectors which constitute a sentence and which have been pre-trained, you feed them through an untrained RNN, and you get a sentence embedding model that performs close to the state of the art. So this is a quite depressing result, actually. And with this we conclude our today's lecture. Thanks a lot.